Greetings, friends, and welcome to further topics on ground. That stuff way down there. So earlier, this is a second in a series. So if you got in out of sequence, I'm offering footnotes to an earlier discussion, and that discussion was ground resistivity expressed in ohm meters. And just what does that ohm meter mean? And this is not the meter that reads ohms. Maybe I should be holding this. My meter that reads ohms, no. It is how many ohms per meter. So Earth being very great in extent, we can think of it as being a series of resistors. And each of those resistors has a value. And I last offered that we were thinking in terms of 100 ohms per meter, which led to some serious consequences when lightning struck. But that was last time. Today we're going to talk about how to lower that resistance, which I'm sure that you're more interested in. Well, we'll put lightning aside. So I'm going to return to that discussion by offering this drawing. And here we have that same 100 ohms specification in a linear meter, but breadth, length, and depth, a cube. And I have illustrated this in 12 resistors so that each resistor occupies an edge of a cube. And we have point X, which is in the upper left back corner of this cube. And we have point Y, which is in the lower right corner of this cube. And the resistance between these 2 points is what we're in. Well, actually it's any 2 points, but as you can tell through symmetry, the resistance between this point and this point with all these interconnections is going to be the same as between this point and this point with all the same interconnections, or between these 2 points. So any 2 adjacent points is symmetrical, and what do we have? 3 different ways. We're going to think of X and Y. Well, obviously, these 2 points will mimic X and Y. These 2 points will mimic X and Y. And these 2 points will mimic X and Y. So between these choices, I've chosen the X and Y. That's the typical, well, it's a standard representation for the Earth resistance. And that, when we work all of these resistors out, it does have a value. There's any number of solutions to this problem, and it's a frequent topic in early electrical engineering courses. But the resistance from X to Y, 83.8 ohms, 83.3 ohms. Not very far from 100. Across one component, well, across a component and all these in parallel, comes up with a similar, but different number, but similar. And in a ballpark, given that the 100 ohms is a very shaky number to begin with, it depends very much on soil type, and that soil type is something that escapes laboratory measurement, in the sense of you being able to go out in your backyard and, well, you could directly measure it, that's for sure. However, Earth is not homogeneous, and it's not always 100 ohms everywhere, even if in aggregate it's an average of 100 ohms. So we're going to discard all those complications and just go with this as you see it. So, well, you'd say, Richard, this doesn't offer me much hope. 100 ohm terminal to the earth ground. If it's the only thing you have, it's the only thing you have. What can I do to make it better, you might ask? That's reasonable. What if you had two in parallel? We all know that by the law of parallel resistance, that there's a formula for that. If they were both 100 ohm leads into the ground, we would have 50 ohms. Bingo. A halving right there. That's pretty simple. What if we do more? Well, if all things being equal, it'll divide by the number of rods that you stick into the ground. But that can lead to a very complex field of ground rods, and you're going to have to connect them all. That's not a debit, and there's guys out there that will drive a rod for the termination of every ground radial that they have for their vertical. More power to them, but it has nothing to do with RF. No, this is just AC/DC at very low frequencies. We'll get into the antenna ground from the antenna's perspective. Very different. But now we're trying to lower the resistance to ground, and we're going to return to my notes. Let's see if I can find them. Here we go. In my notes, we have this, again, REA Bulletin 1751F-802. This is from the Department of Agriculture. So they know their dirt. Here we visit all of the minimum and maximum resistance ranges. This is why I said this 100 ohms was a dicey choice, because for any particular soil type, the ranges are monumental. What can I say? You can measure it. You can measure it. There's ways of measuring it. But we're not going into that right now. And we're going to put this table aside, and we're going to go into soil moisture. As it says here, nearly any soil with a 0 moisture content is an insulator. And that is bad news. That's for hams that live on top of a mountain. You might as well. You go for horizontal antennas or build massive radial systems, because you're not going to find pounding any number of ground rods is not going to bring you much relief, unless that mountain you live on is a lot of cracked limestone and percolates well. I discussed that the last time. So here we come to this proviso. It should be noted that above 17% moisture by weight, additional moisture has little effect. Below this figure, resistivity rises rapidly until at 2% moisture it reaches 100 times its value at 17% moisture. So that is a nonlinear relationship there, where we go 2 orders of magnitude in just 1 order of magnitude change, which is we go from 2% moisture to, well, call it 20% moisture. That's a factor of 10, but the resistance changes by 100. So this is a very nonlinear curve. So if the question on the table is how do I improve my ground situation, well, you'll water it, but that only goes so far. If you live in dry country, that might go quite far, but how far does that water penetrate? It's going to have to go quite deep. So we're going to move on and just consider what the hand has been dealt, considering the soil resistivity. We live with it. The moisture content, we're not going to change that much, but we can slam a rod into it, or we can bury horizontal rods, not slamming it in, but laying it into, say, a ditch, and then backfilling the ditch. Cut and cover kind of situation. I'm not going to go into that. But in this portion of my notes, we have vertical ground electrodes. We have this formula, the single vertical ground electrode. When I drove my, in our last discussion, when I drove my stake into the ground, I simply declared it as being 2 meters long. That is, let's see, length, right there. Whoop, okay, that's not what I need. Right here, electrode length. Also its diameter, and then various pi, and the earth resistivity, which we have to find from the table. Plugging in the numbers yields us this R, this RR, the electrode resistance to ground in ohms. We're no longer speaking of ohm meters, we're now strictly in ohms. This is like you have 1/2 of a resistor, you have its lead, and you trust that the other lead is going to a massive steel block that you can attach to. And when we achieve that for here we go, for a 5 ohm resistive ground and 2 meter length rod of 2.5 centimeters diameter, 1 inch, we can achieve a ground resistance of 2 ohms. Well, this is much better than 100. However, what did I use for, okay, I said 5 ohm resistive ground. If we go back to that chart, that is the sweetest of all deals and is highly unlikely. If we bump that up to a 50 ohm resistive ground, the ground resistance climbs to 22 ohms. If the resistivity of the soil is 500 ohm meter, then we have a 217 ohm resistor lead sticking out of the ground. And if, for instance, we have a lot more rock than we do have clay or soil, well, we now have a resistor to a 2,170 ohm resistor. Well, we have a lead to a 2,170 ohm resistor. Far, far, far worse than my original 100 ohm sample. But all of this is representative of some amateurs' experience in their locality. Now, what does the length, well, let's go back up to here. Well, notice that length appears here and length appears here. So it is a very prominent feature of how much resistance we might find from its being buried into a soil type. We looked at one length right here, 2 meters. But if we go down to this chart, this will reveal some the average earth resistance of 140 ground rods. So this is 140 different ground rods that have been measured in place. And like I said, you can measure it yourself. It's simple to do. It's moderately complex. It's not instrumentations that you have available commonly. And that's why we use these other people's work, as in this chart here, which reveals for a 5-foot length of rod, which is to say it's buried 5 feet deep, it exhibits 66 ohms of resistance to earth at that point. And again, the other point is the remote leadless resistive side of Earth that's infinite. If we were to double that depth, we pretty much have the resistance, 29.8. If we go out to 15 feet deep, or a 15-foot long rod buried, sunk right to its last inch, it's exhibiting 12.9 ohms. A 20-foot length, 7.7. A 25-foot length, 6.6 ohms now, 6 ohms. We've come down to 1/10 of our value here for 5 foot at only 5 times the length. at only 5 times the length. I'd like to see you pounding in a 25-foot ground rod. This leads us to practicalities. It's rare that you're going to achieve this value, much less this value. And you might find service in this value in many stakes into the ground instead of going for, say, 10 stakes in the ground instead of just one 25-foot stake into the ground. Why do I say that? Well, this is just matters of practicality. So what else do we have to say about that? Here we have buried bare wire. Now I'm not going to use here. This is yet another formula that yields even other answers. Whoop! That was getting a little wild. So for that same 5 ohm resistive ground, and now a horizontal 2-meter length rod of 2.5 centimeter diameter, 1 meter below the surface of the soil, I'm getting a resistivity, or earth resistance, of 1.77 ohms. This is not ohm meters, this is ohms. When current goes into that lead, you can expect it to elevate in potential through good old Ohm's law. If it was for a 50 ohm resistive ground, well, we see 17 ohms of that. For a 500 ohm, we see 177 of that 500 resistivity ground. And likewise, for 5,000 ohms, we see 1,770 ohms. So that's a blasting through all the different ways to look at ground at the finer details and how this package of resistors works out as a model, a representation for ground, where you can attach only to the one point, the X point, say. Let's return to that drawing. So basically, X is that little stub of the rod that sticks above the ground for you to access it with a clamp. And by clamp, I mean something that tightens with a bolt to its perimeter with a wire attachment to it also. This is called bonding. And clips, nothing semi-permanent or lackadaisical. That's outside the code, so don't go there. We're speaking of a wrench-tight bolt-on connections. This is hardware that you can find in any department store. So again, that's the accessible point. Why is the infinite ground somewhere else? And we know that this cube is not in isolation. There's cubes occupying ground in depth, breadth, that makes this a much more complex circuit, but it still yields from the X to the Y 83 ohms. And you've seen how that 83 ohms arrived through various different soil types or ground rod depths. So I felt a little necessary to finish up the topic of AC and DC ground, and with some formulas, some practical numbers to show you the relationships and how that ties into the diffuse nature of the ground being this block of resistive material that gets between you and the infinite sink of electrons that we rely on coming from ground. So I hope you got something out of this. And there's more to say. We'll go into more complex features later, but that pretty well covers it for the AC and low frequency AC, and the DC considerations of earth ground. So we'll get to antennas eventually, and here's a teaser. We'll get to variable transmission lines to tune them. I hope you can find that when I. This is still a future project. I hope you stay tuned. So 73s.